Hello, everybody. So here is our second section on our fourth unit. It'll be mostly on chapter 4, but there is one section from chapter 3 that we're going to squeeze in tomorrow. So the last lecture was on exponential functions in general. So here we are switching to the inverse. And remember properties of inverses. There's several, but the big idea is that inverses undo each other. So addition will undo subtraction, etc. So you have exponential functions. Well, what will undo this operation? A logarithm will. And one of the consequences is that the domain and the range switch. So if I asked you to find the inverse of this, your first step would be to switch x and y and then solve for y. Well, to do that, you would get this. So a couple hundred years ago, a mathematician kind of invented this terminology, and they called it logarithm, and they just defined it as the inverse of this. So a lot of things in math are invented to serve our purposes. So we know exponential behavior exists, and we want to undo it. So we call it a logarithm. And the big consequence is everything gets switched around, the domain and the range. So exponential functions can receive any x value. You could put any x value into the exponent. That means that the inverse will put out any value, any real value. So the range of a logarithm will be all real numbers. Back to exponential. What will the exponential produce? Well, remember, b is positive. It can't be 1, but it is positive. And x could be anything, negative, positive, 0. But if you start with a positive base, no matter what you raise it to, you will always end up with a positive number. You won't even get to 0. So this exponential function doesn't even have a 0, an x-intercept, because there's no x value you can plug in to make this equal 0. It's always going to be positive. But don't get too strict there, because I could just drop this function down 3 units, and then suddenly the range is from -3 to infinity. It's this portion that has a range from 0 to infinity. Okay. And since the exponential function will only produce positives, that means its inverse can only receive positives. So this right here must be positive. Otherwise, the logarithm would just be undefined. Back to the exponential, it passes the horizontal line test. So that tells us that there is an inverse, which is this right here, this logarithm. All the xy's, all the ordered pairs, if you were to switch them and plot them, you would get this blue graph. And if you were to graph both of these in the same plane, they would be symmetrical to the line y equals x. All right. As x approaches infinity with this one, so when x gets really, really big, this exponential function, the y values also get really, really big. And when x gets really, really small, so in other words, going to the left, the y values get really, really close to 0. So they approach 0. On the logarithm, first of all, remember the logarithm's domain is not all real. So it begins past 0. So keep that in mind. But to finish this off, when x gets really, really large, what is happening to the y values? Well, look at the range of the logarithm. The range goes all the way down to negative infinity and all the way up to positive infinity. So the range is just going to keep on going up as x gets bigger. So the y approaches infinity. But I can't say when x goes to negative infinity, because this logarithm doesn't even know what x equals -3 is, let alone negative infinity. So how can I describe the end behavior of this? Well, when x gets really, really close to 0, but from the right. And we have notation for that. X approaches 0 from the right. What happens to the y values? Well, the y values go down to infinity. And it's worth looking again. You can kind of see the domain and the range here. Like on the exponential function, I can talk about x going to infinity and negative infinity. That's the domain. The range, however, the y goes to 0, y goes to infinity. So that's telling me the range. And similarly for the logarithm has a domain of only from 0 to the right of 0 and to infinity, and its range is all real numbers. Let's practice converting from exponential to logarithmic, and then we'll reverse that, and then we'll evaluate, and we'll graph, and then that'll be pretty much it. So how do I convert from logarithm to exponential, from exponent to logarithm? This is reversed. Okay, sorry about that. So converting from exponent to logarithm. So 2 to the 4th equals 16. So 2 is the base. That is going to be the base of my logarithm. And 4 is the exponent. So that is what the logarithms produce. 16 is the power, so that is what the logarithm receives. So what it produces, the exponential, is what the logarithm will receive. And the exponent is what the exponential function receives. Well, that's what the logarithm produces. So I always like to say logarithms are exponents. So when you think about logarithms, they're exponents. So in this situation, the exponent is 4. So whatever your logarithm is, it's going to equal 4. You might think the same thing here. The exponent is 3. So whatever the logarithm will equal, it'll equal, whatever the logarithm is, it'll equal 3. But there's a problem here. And the problem is that this exponential function is producing a negative number, and that's not possible. So the base is always positive for exponentials, and you can't take a positive number, raise it to 3, and get -8. That's just impossible. So there is no logarithm for that. This is out of the domain. Here, however, the exponent is x plus 4. So whatever my log is, it's going to equal x plus 4. And logarithms have a base, log base 12, the same base that supports the exponent. So log base 12 of 55 equals x plus 4. Here, the exponent is a half, so the logarithm is going to equal a half. The logarithm of what? Log base 9, the same base that supports the exponent. Log base 9 of 3 equals a half. And again, the exponent is x, so the logarithm is going to equal x. This is log base 10 of 0.991, but this is a special log. Whenever there's a log base 10, this is called a common log. The 10 is just not written. So this is how we would write them. If it is a log base 10, you just write the word log. This is a convention that we just have to get used to. And we're already used to conventions. Like I could go to an Algebra 1 student and say, what's the coefficient? And they would say 3 because I could see a 3. And I say, well, what's the coefficient here? And they would say, hopefully they would say 1. Even though we don't see a 1 here, it's just by convention. We know that there's a 1 there. A similar argument here. When you don't see the base, we have to know that it is base 10. And here's another irregular situation. E, which is just a real number between 2 and 3. E to the x is 441. Well, the exponent is x, so the log is going to equal x. Log base E of 441. But this is another irregular log. This is called the natural log. So you would never write log base E. It is ln. ln is log base E. ln is the same thing as log base E. How about reversing them? If I give you a log, can you put it to exponential form? Well, remember, logarithms are exponents. So this log equals x. X is the exponent. That's going to go on this base. So it's going to be 1.5 raised to the x equals 5. And I remember learning this. They called it the circle method. So you start with the base and you wrap around. This is the exponent. And you complete the circle, and that equals 5. 1.5 to the x equals 5. Here, the base is x minus 3. So x minus 3 raised to 13.1 equals 908. What do I do here? Remember, this is a common log. There's no base I can see, but that means it's base 10. So this is 10 to the second equals 100. And again, another ln is the natural log, and this is the base e. So e to 3.434 equals 31. Evaluate. So find the value. Okay, sorry about that. So log base 3 of 415. We need to know how to do this on the calculator and without a calculator. So log base 3 of 415, logarithms are exponents, so I need to be thinking what exponent could go in 3 that would result in 415. Calculator can handle it. You have to find your log button, and down here on the left-hand side, notice how e to the x and ln are next to each other. That is because those two are inverses of each other. And the ln is natural log. That's the log base e. And so to do this, if you type in log, this was log base 3 of 415, I think. Yep. And I get 5.48718. Remember, logs are exponents. So this number, this is the exponent that would go in 3 that would result in 415. And just to test it out, 3 raised to the 5.487 gets me darn close to 415. So 5.487 would be my answer. Whoops. Okay, another one. Natural log of 9 plus the log of 177. So this is just calculator work. So I had to find natural log. The natural log of 9. Close the parentheses. Plus the log of 177. I'm not going to like that. Let me just, probably a way to do it without putting in that 10, but 4.445. And then finally, log base 5 of 35.7. Let's think about this. Logs are exponents. So what exponent goes on 5 that results in 35.7? Well, it's bigger than 2 because 5 squared is 25, but it's smaller than 3 because 5 to the third is 125. So 2 point something was going to be our answer here. And I do log base 5 of 35.7, 2.221. All right, without a calculator, this log base 3 of 9. So logs are exponents. What exponent would go in 3 that would result in 9? 2. I have log base 3 of 9 children because I have 2 children. Log base 5 of what? I'm sorry, log base 5 of a fifth equals what? So 5 to what power is a fifth? 5 to the negative first power is a fifth. Remember, raising it to the negative would flip the base. And then log base 4 of 1 equals what? So what exponent would go on 4 that would result in 1? And that, of course, is 0, because for anything to the 0 equals 1. And then lastly, log base 4 of 4 to the 3x equals what? So this is impossible to do in a calculator since our calculators can't receive x, an unknown. So what exponent would go on the base 4 that would result in this? So what would the exponent have to be so that when I put it on 4, I get this? Well, I hope you can see that it is 3x, because if I take 4 raised to the 3x, I will get 4 to the 3x. Can we graph these with just the slightest information about transformations? So here is log base 3 of x, which is the inverse of 3 to the x. So here is 3 to the x and its inverse, log base 3 of x. And notice how they are symmetrical on the line y equals x. Also notice how exponential functions, they all have a horizontal asymptote, right? Well, in the inverse, everything switches. So if there's a horizontal asymptote on the exponent, there is a vertical asymptote on the logarithmic function. All right, what transformation is going to occur here? This x plus 2. That's going to take this and shift it to the left 2. Notice this also changes the vertical asymptote. Now for the purple function, the vertical asymptote is x equals negative 2. It still has a range of all real numbers, but its domain is from negative 2 to infinity. X minus 5, we'll just take this function and move it to the right 5. It changes the vertical asymptote from x equals 0 to x equals 5. Plus 2 outside of the operation will raise it up 2. It does not change the vertical asymptote because you didn't go left or right. It doesn't even change the range. The range is still all real numbers. Just lifting it up 2 units doesn't change the range. What does this do? Replace all the x values with their opposites, so that will reflect it over the y-axis. So now the domain is from negative infinity to 0. Still has that vertical asymptote at x equals 0 because I didn't move it left or right. 2 times the logarithm will multiply every y value by 2. So it'll just stretch this. This right here, 1, 0. If I multiply the y value by 2, it'll still be 1, 0. This ordered pair looks like 3, 1. So if I multiply this y value by 2, it'll become 3, 2. And so I still have this this x-intercept of 1, 0, and notice 3, 1 became 3, 2. This right here looks like 9, 2. It becomes 9, 4. You're doubling all the y values. And then multiplying all the y values by negative 2, we'll just flip it upside down and stretch it by 2. Still has that vertical asymptote, still has a range of all real numbers. And then our last slide. No, 2 more to go. What do I know about this logarithm? First of all, the domain. What can x possibly be? This has to be non-negative. So x plus 7 must be greater than 0, which means x must be greater than negative 7. That's the domain. As an interval, it's from negative 7 to infinity. For the range, for all logarithms, the range is always all real. So from negative infinity to infinity. Asymptotes, logarithms have a vertical asymptote, and this one occurs, normally it's when x equals 0, but this one got shifted to the left 7. So now the vertical asymptote is x equals negative 7. Does this have a y-intercept? Well, the y-intercept always occurs when x is 0. So if you plug in 0 for x, what do you get? You get log base 2 of 7 plus 3. You could put that in your calculator if you want, or you just leave it like this. X-intercept. The x-intercept is always when y equals 0. So if you let y equal 0, what will x be? Just a little bit of solving. So I'd have to get x by itself. Let's subtract 3 first. And then now what? This logarithm equals negative 3. Logs equal exponents. So negative 3 is the exponent on 2 that will result in x plus 7. So 2 to the negative third equals x plus 7. What is 2 to the negative third? It's 1 over 2 to the third. So it's 1 over 2 times 1 over 2 times 1 over 2. So it's 1 over 8. And then you subtract 7, you get negative 6 and 7/8. And so there is an x-intercept, negative 6 and 7/8, comma, 0. And then finally, we have something about electric eels, and the length of the electric eel is connected to the weight of the eel by this logarithm. So what is the length of an eel that weighs this many pounds? So I would plug in 14.4 into W and just put this into my calculator directly, and I discover that it's about 31 inches long. An electric eel that weighs this much would be 31 inches long. There was an eel found in the sea lately that was 29.5 pounds and was this long. How does that compare to our model? Well, 4 feet 1 inch, that is 49 inches, because there's 48 inches in 4 feet. And then I could just plug in 49 inches for my length. Sorry, plug in. Okay, so 49 inches long. I know the weight is 29.5. The function up here depends on the weight. So I'm going to plug in 29.5 into W. And according to the model, the length of an eel that weighs 29.5 pounds would be a little over 47 inches long. So the one that was found was 49 inches long, pretty close. If we found that one that's 31 inches long, how much can we expect it to weigh? Well, now we know the length, so that's L, so that goes here, the dependent variable, and I need to solve for W. So I need to undo all these things. I need to do the inverse of subtracting, which is adding 28.7. The inverse of multiplying 22.4, that's dividing by 22.4. The inverse of the natural log. So natural log is log base e, and logs equal exponents. So this exponent is on the base e. E to the 2.66517 will equal W. Go to your calculator and you get about 14.37. So that eel should weigh a little over 14 pounds.